All right, welcome back everyone. This is the Calculus 2. So in this video, we're gonna do the last lecture, Recording 6.1, Power Series and Functions. So this is part of your final exam. And then, it's a very short topic and very similar. There's a lot of similarity from chapter 5. We've been, organizing and, identifying whether it is a convergence and divergence. So it's a similar chapter 6. Just a little bit of, heavy duty, long expression. So let's take a look at what the definition of power series. Okay, so let me go to show you the definition of a power series. So first of all, we need to know there are so many different types of series that we have learned since chapter 5. So whenever you have a different type of series, please define what the form look like and what the definition of each different series. So power series, let me highlight it. Okay, it's a very interesting. So it has a center point. So what I'm saying is, let me show you the example. Let's say I have infinity n equal to 1, and let's say I have x to the n. So we know this is the summation. So it is a series. That means you're gonna adding when x equal to, let's say it's a beginning 0. So x to the 0, you're gonna adding the next number, you're gonna adding the next number, you're keep increasing up to infinity. And then obviously you see that this is a geometric series because you're keep multiplying x to find out the next number. So what the power series, you have a same story, from the general series definition. Now I just have a C coefficient, okay, in front of the x to the n. So what's happening? This means I'm gonna just create a new one. So I'm gonna copy this, copy and paste here, and let me minimize a little bit. What happened is you have a coefficient right in front of the variable x, let's say C, okay? So whenever you're gonna find out the term, the partial term, there is gonna be Cn all the time, isn't it? So this particular form with the coefficient, and then it is based on the geometric series, we call that is a power series. Okay, so make sure there is a unique coefficient. It's always a fixed. So x to the n form, and then you have a coefficient. So this is x to the 0 is always 1. So this is going to be c to the 0, c to the 1 times x to the 1, c to the 2, x to the 2. So we call this form as a power series. Does it make sense? Very simple, just we are expanding our knowledge from the general form of the series. Just we are adding the coefficient, okay? So now, this is the case where the center at x equal to 0. So what does it mean center at x equal to 0 and x equal to a? So here, you can have, coordinate points. So this is x, but now I'm gonna subtract x minus a. So that means center at x equal to a. So it's gonna be same pattern. You're gonna keep increasing x minus a to the 0. You have x minus a to the 1. You're keep increasing, but then what happened? You have a unique coefficient C0, C1, keep going on. And obviously, it is also geometric series. You're keep multiplying x minus a to find out the next one. So that's the definition and form of the power series. We have a unique coefficient right in front of the variable x. So there's a two case where the center points at x equal to 0 or at x equal to a, because we could, have many different, coordinate points. So this is the power series you can think about. So I'm going to change this color. Okay, so that's the power series. And now we have all the time have the same question, whether this power series is a convergence or divergence, right? So since this power, series, so let me now bring this one here, and then I'm gonna bring this here. So let me minimize a little bit. So this one was infinity Cn x minus, I need a space, x minus a to the n, right? So we have those three, geometric series, because you keep multiplying same number x or x minus a, x minus a, x minus a. So this power series is part of the geometric series we just observed, right? Because you keep multiplying same number, right? So therefore, to determine whether the power series is diverges or converges, we need to see the geometric series characteristic. Does it make sense? So my writing is too long, but you see what I'm talking here. Characteristics. So since the power series is a part of the geometric series, so we are trying to determine whether power series is divergence or convergence. To see that, we need to see the geometric series characteristic. So what the geometric series characteristic to determine whether the geometric series is convergence and divergence? Do you remember the formula? A over 1 minus r, if you have certain number, always that geometric series is a convergence. Do you remember? So the A means the first number, 1 minus r, r means the common ratio. So we are going to utilize the same concept to determine whether the power series is a convergence or divergence. Does it make sense? So especially, right, a 1 over 1 minus r, if you have a particular number of that outcome is a convergence. So let me give you the real problem based on that concept. So that's a little bit of concept you need to recall. So here is my real problem. Let's say I do have power series, looks like x minus 3 to the n over n. So take a look at it. We are going to find the x interval where this power series is going to be converges. I want to find out which x interval. So this x. So x should be a particular number. We don't know yet, but when x is in certain interval, this entire power series will be convergence all the time. So check it out. Is it really power series? So I'm going to modify this. This is going to be, right, infinity n equal to 0. I'm going to separate this fraction top and bottom. So 1 over n times x minus 3 to the n. This is definitely power series, right? Why? Because I have a variable and I have a coefficient 1 over n is a constant. So this is the coefficient. And then especially this is where centered at x equal to 3. That's the definition of this power series according to this form. So this power series, yes, I see the unit coefficient 1 over n in front of x minus 3 to the n, and then it is centered at x equal to 3. So, okay, that's good. So I want to know now whether this is divergence, convergence. They say it must be convergence If it is a convergence, when it happened, when which x interval gives you that power series become convergence. So you guys are following that logic, so far so good. And then here is the key point. Power series, you always consider to use a ratio test. So this is an important thing because we learned so many different tests in chapter 5 to determine whether it is a convergence or divergence. So it's power series, you're going to think about the ratio test. So that's something we can utilize it. So by using, I hope you don't forget what the ratio test. By using ratio test, we can see if whether the power series is convergence or divergence, correct? So let's go back. What the ratio test was. I hope you didn't forget. Do you remember? The ratio test says you have infinity an, and then you are going to go back to the last lecture note. You're going to take the limit of an plus 1 over an, right? That is a p. If that p is between 0 and 1, then what? The power series, then this ratio test help us to find out this series is always a convergence. So that was the definition of the ratio test. So I'm going to highlight it. Right? So we're going to utilize this ratio test. Are you okay with that? I'm not creating this theory. This is 5.6. We learned ratio test. You're going to absolute value and divide it by an plus 1 over an, take the limit, and then look at the size of p. If that is between 0 and 1, then that series is a convergence. So we're going to do that work. Because I want to know this power series is a convergence or not. So here we see an is given, right? X minus 3 to the n over n. That means an plus 1, x minus 3 to the n plus 1 over n plus 1. Are you okay? So we have an and an plus 1. I'm going to take the limit. An plus 1 over an. That means take the limit. An plus 1 times 1 over an. Same thing. So we're going to do take the limit. An plus 1 is what? X minus 3 n plus 1 over n plus 1. And 1 over an, we're going to flip this. So n over x minus 3 n. Okay, keep going. Limit. I can separate it. X minus 3 to the n, x minus 3. Are you okay with that? Because that's n plus 1. And then we have divided by n plus 1 times n over x minus 3 to the n. So I see the cancellation. Where are you? X minus n 3 to the n. This is cancel. And then let's write down the rest of information. We have x minus 3 over n plus 1 times n. I can rewrite it. So let me minimize it a little bit. So it is going to be, I can change the order. That means x minus 3 times n over n plus 1. So what I'm going to do, the x minus 3, that is kind of like a constant. I can bring this one to the front because n is approaching to infinity. So you can solve x minus 3 limit. We have n over n plus 1. So dun 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 dun. Now they have a top and bottom same coefficient, n to the 1, n to the 1. So you are just reading the leading coefficient. This is going to be invisible 1. This is going to be just 1 over 1 is 1. X minus 3 times 1, that is x minus 3. So what is that? This is your P. So we know, we found out P equal to x minus 3 so far. Are you following? And then ratio test, I just talked about it. Ratio test said if P is between 0 and 1, then the series is a convergence, correct? So therefore, that's your P. That P is x minus 3 must be between 0 and 1. I'm looking for the interval of x. So therefore, what happened? You're going to solve the inequality, adding 3 everywhere. So what happened? When x is between, am I calculate correctly? 1 second. I think I have a little bit typo. Let me double check. So P is between 0 and 1. And then I have to be careful. So you see that when I take out the x minus 3, I forgot the absolute value because that should be part of it. So there's must be absolute value still live there. So P was absolute value. That was my mistake. So let me just go back to the question just a little bit here. So what I'm saying is we found out P is absolute value of x minus 3. And then we know that P is between 0 and 1. So we're going to work on that. So that means absolute value x minus 3 is a less than 1. Because we don't need to consider 0 because anyway, this is a positive, but less than 1. This means absolute value, when you get rid of it, it's going to be between negative and 1. That's my mistake at the beginning. But now we got that one. So let me just minimize a little bit. Okay, so now you are going to adding 3. So when x is between 2 and 4, this series is always going to be convergent. So what I'm saying is, we had a question, this one, 1 over n, x minus 3 to the n. I want to know the x, the possible x that makes this series convergence all the time. So this power series is convergence series when x is between 2 to 4 all the time. So when x equal to 2.1, 2.2, less than 3.9999999, this power series always a convergence. So that's the theoretically you can solve it. I hope this is not crazy work, just a little bit of thinking step. So our goal is to not only just determine this power series is convergence. I want to find out the particular axis that makes this power series become convergence series. So therefore, by using the ratio test, you can find out the size of P that the series is convergence, and then the P was absolute value of x minus 3, so that you can solve for less than 1 and 1. That's a less than case of the absolute value. So that when x is between 2 to 4, you always gonna get a convergent power series. So that's the main idea of 6.1. Okay, so take a look at it. We're gonna practice a couple more, but I'm gonna hold up because I want to make sure you got this. So I'm gonna hold up here. Are you guys okay? Okay, I love to see your thumbs up. Anybody has a question? So I'm gonna take a look at a couple more examples. So the theory is pretty simple. Okay, I'm gonna go down slowly. So this is the convergence of power series. So we check that. So this is a little bit of like a long sentences, but the way, consider you have a power series and you want to find out the possible x's that makes this power series either convergence or divergence. You're always going to use the ratio test. And then find out the size of P. If that P is between what? 0 and 1, right? It's going to be convergence. If it is a, less than or greater than 1, then it's going to be the divergence. So just keep in mind the same idea, but we're going to take a look at one more thing here. So you're going to have a P by using the ratio test, which means absolute value of that is a P. And then that P, you will find out the absolute value of x minus a, something we just found out like here. So what I'm saying is simply absolute value x minus a is less than, it is going to be convergence. If the x minus absolute value is greater than, it is going to be the divergence. So we just talked about the same theory, but I'm going to show you the example. So there's another approach as well, but I think using the ratio test is much simpler. So let's take a look at a couple more examples. So let's look at it. We're gonna just keep using the ratio test. Okay, I wanna find out the possible x's. This power series, this is a power series. Why? Because it means you have a unique coefficient 1 over n factorial and x to the n. You see that coefficient times x to the n. This is the power series centered at x equal to 0. So I can change that order. Right, this is that, and this is the power series at x equal to 0. So I want to find out this power series is going to be the convergence, right? When? That's my question. When? Which means you're going to find out the x interval. What x's make it possible, all the time convergence series? So according to the ratio test, let's find out the P. So we know this is your an, right? X to the n over n factorial, an plus 1, x to the n plus 1 over n plus 1 factorial, correct? So we have that information. So the limit and approach to the infinity, we have an plus 1 over an. That means an plus 1 times 1 over an. So we have all the information. An plus 1 over n plus 1 factorial times flip of an. So n factorial over x to the n. So we need to simplify this all the time. Yeah. So let's take a look at it. It means what? X to the n times x over, whoa, this part, n plus 1 factorial. Do you remember? N plus 1 factorial means n plus 1 times n minus 1 times n minus 2, all the way down after n plus 1, that's n factorial. Therefore, n plus 1 factorial, same as n plus 1 times n factorial. So I can say this one, n plus 1 times n factorial. Got you? Then times n factorial over x to the n. Dun, 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 dun. All the cancellation. N factorial, x to the n, bye-bye. So now we have n infinity x over n plus 1 remaining. Again, I can bring x into the front. So absolute value x, limit, we have 1 over n plus 1. So what happened? Now, what is the evaluation of the limit here? So this is going to be 1 over infinity plus 1. This is going to be smaller, getting close to 0. Do you remember? Limit of 1 over infinity, it's a 0. So absolute value 0, this is your p. Correct? And then I want to find out the power series is always a convergence. So what happened is we have to think about very carefully. What do you guys think? No matter what x, right? No matter what the x, this is always a 0, isn't it? So no matter what you multiply 0, it's a 0. So p is actually 0, right? So the p is definitely less than 1. So go up. This is a p. P is a less than 0, right? Is always a convergence because we absolutely have the number. So what I'm saying is p equal to 0. So the power series is a convergence, or you can say power series converges to 0. But I want to find out the x interval. So what x? Doesn't matter whether x is a negative number, positive number, 0, because you anyway multiply 0, x can be any number. So x can be any real number, negative infinity to positive infinity. So therefore, my conclusion is this power series, infinity from 0, x to the n over n factorial, this is the convergence, right? When x is negative infinity to positive infinity, because x can be any number. Anyway, you're going to multiply 0. So we are not looking for the size of p. We are looking for the interval of x. So x can be any number. So the same thing here, when x is between 2 to 4, this power series is always a convergence. So therefore, because it can be equal to 0 to 1. So it's a 0, it's a convergence. So therefore, x can be any real number. That's how you got this question. So I'm going to hold up here. Does it make sense to you? So I'm going to hold up here. This is a very funky question and very, neat question. You can think about it. So if you got this one, I love to see your thumbs up. So we're going to do a couple more questions like that. Okay. So think about it. It's not like a crazy logical question. You can definitely handle it. But let's take a look at another one. So I'm keep utilizing the ratio test to find out the x interval. So here's the same thing. I do have a unique coefficient. And this is definitely power series centered at x equal to 0. Don't you think so? So I want to find out the possible x's that makes this power series convergence. Correct? So this is power series centered at x equal to 0. So we know an. We're going to utilize the ratio test, an. We have n factorial x to the n, an plus 1, n plus 1 factorial, x to the n plus 1. Dun, 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 dun. We good. So the ratio test help us to find out the p. So take the limit a n plus 1 over an. So now you know limit an plus n plus 1 factorial times x to the n plus 1 times, right? This is an. And then you're going to flip over an. So 1 over n factorial x to the n. Correct? So I don't need to write down the dot here. Oh, 1 factorial x to the n, right? So now we know the fact n plus 1 factorial is n plus 1 times n factorial. So therefore, you can rewrite it. What happened? N plus 1 factorial, n plus 1 times n factorial times x to the n, x to the 1, right? So this is x to the n plus 1 means x to the n times x. And then n plus 1 factorial is, you can see the structure. This is this one times n factorial, x to the n plus 1, x to the n times x. And then I'm going to multiply n factorial x to the n. Why am I doing this? Because we see this cancellation. So all the x to the n, bye-bye, n to the n factorial, bye-bye. So you have, what is the remaining stuff? What are the remaining stuff? You got limit n plus 1 x. Again, I can bring up x to the front and then absolute value limit n plus 1. So we are trying to evaluate this limit. What happened? This is infinity plus 1 is infinity. So what happened? No matter what you multiply with infinity is infinity. So this p-value is actually divergence. This is a greater than 1. So we are looking for, so this is infinity. We are looking for the possible x. I want to make this power series is a convergence. So what is the case when, what do you guys think? When x equal to 0, then 0 times infinity will be 0, then it's going to be convergence. You cannot have any other x's. So what I'm saying is this power series n factorial x to the n convergence series when only when x equal to 0. That's the answer. Does it make sense? So we are looking for not the size of p. We are looking for the possible x that makes this power series become convergence series all the time. So that when x equal to 0, obviously everything is going to be 0. The p size is going to be 0. So therefore, to become convergence power series, x must be 0 in this case. That's the only possible answer. Okay. I think we are getting better and better. Are you guys okay? So I'm going to do 2 more examples like that because it's very important. So if you got that one, let's take a look at it. I'm going to wait for you for a second. How's it going? All right. If you got that one, I love to see you guys invisible thumbs up. All right, you got this, you got this. So I hope you're getting a better confidence. Let's take a look at the next question. Here we go. So I see this is a power series, y. This is a unique coefficient, and then I see it's centered at x equal to 1. So I want to make this power series become convergence. And I'm looking for the possible x's. So this is definitely power series centered at x equal to 1. So we're gonna keep using ratio test. So an 2 to the negative n over n plus 1, x minus 1 to the n, an plus 1, 2 to the negative n plus 1 over n plus 1 plus 1. X minus, not equal, x minus 1 n plus 1. You got it? So according to the ratio test, so take the limit. We have an plus 1 over an. So that means what? An plus 1 is this 2 to the negative. I can do the distributive property, negative n minus 1 over n plus 1 plus 1, n plus 2. And then we have x minus 1, n plus 1. So this is an plus 1. So let me minimize it. And then you're multiplying what? The flip over the an. So if you flip over, the bottom is going to be 2 to the negative n. And then x minus 1 to the n in the bottom, n plus 1 in the top. So that's something you can get it. Now, I'm going to try to simplify so that I can cancel top and bottom. So let's take a look at it. This means limit negative 2 to the, not negative, 2 to the what? I can separate this is going to be 2 to the negative n times 2 to the negative 1 over n plus 1. And then we have x minus 1 to the n, x minus 1 in the numerator. Are you following? So this is a green. This is a blue. Oh, I like the blue. I feel like we are, I don't know, I'm missing the summer, right? This is spring or fall. I don't know, it's a bit long, right? We are missing summer. So anyway, this color reminds me. And I do have a 2 to the negative n, x minus 1 to the n, n plus 1. Oh, what's going on, guys? Oh, actually, I had a little bit of typo. This is n plus 2, my bad. All right, where's the cancellation? 2 to the negative n, x minus 1 to the n. That's it. That's all we cancel. And let me write down the remaining stuff. So the limit 2 to the negative 1, x minus 1, right? And n plus 1 in the numerator over n plus 2. Great. Now, except the n, right? Because n is approaching to infinity. I'm going to bring all the constant to the front. So it is going to be negative 2, why negative 2? 2 to the negative 1 and x minus 1 limit n plus 1 over n plus 2. But I think I need a space. So that's it. And then we're going to evaluate the limit because the top and bottom, they're same coefficient. Do you see that? The degree is 1, n to the 1. The numerator degree is n to the 1. So we are just reading the coefficient 1 over 1. This limit is going to be found as 1. So we have now 2 to the negative 1, x minus 1. That is going to be times 1. That's it. So which means 2 to the negative 1, x minus 1 remaining. Okay, so now I'm going to change 2 to the negative 1 means 1 over 2, x minus 1, correct? That's your P. Dun, 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 dun. Good, that's your P. Are you guys okay? So what happened? When size of P is between 0 and 1, but make sure this is absolute value. So when the absolute value P is less than or equal to 1, then whatever the given power series, right? That's going to be convergence, right? So therefore your P is 1 over 2 x minus 1 is less than or equal to 1. So what happened? This means inequality between -1 and 1, x minus 2, 1 over 2, x minus 1. So we are solving x here. Are you okay? So I'm going to multiply 2 to 2 so that I can get rid of the fraction 2. So -2, x minus 1, positive 2, adding 1, adding 1, adding 1. So -1, x 3. So what happened? When x is between -1 and 3, right? So when it means the power series, we had a long one, 2 to the negative n over n plus 1, x minus 1 n, converges when x is -1 and 3. That's kind of our final answer. But here, sometimes you need to check. However, we need to really check the inclusiveness of the ending number, whether we really include -1 and 3. So okay, we are 100% sure x can be -1 point, -0.9, 0.0.9, 1.11111, 2.22222 up to 3. But what I'm saying is we need to check. Here we have a 2 scenario. Check x equal to -1, x equal to 3. So we have the power series looks like 0, and then 2 to the negative n over n plus 1, -1, x minus -1. I'm gonna plugging in -1 here, okay? Let's see what's going on. So x is here, so this is a number, doesn't matter. So 2 to the -1, yeah, so -2. So this is going to be 2 to the negative n, n plus 1, -2 to the n, right? And I know this part is the same as -2 to the, you can rewrite it, -1 to the n. Oops. You have a -1 to the n times a 2 to the n. You can separate it. So this is the same meaning, -1, or yes, you can rewrite it this way, -1 to the n, 2 to the n. They are same thing. So what I'm saying here, they're same. So I'm going to modify a little bit. So we almost done. 2 to the negative n over n plus 1. And then I'm going to write it -1 to the n, 2 to the n. Right? And then this 2 to the negative n, we can flip. 1 over 2 to the positive. So make sure the reciprocal, you can flip, n plus 1 still there. And you have a -1 to the n, 2 to the n. What I'm doing is I try to cancel. So at the end, what is the remaining? -1 to the n over n plus 1. This is what? This is plus minus alternating harmonic series. Do you remember? Alternating harmonic series, if you keep adding, they're getting close to 0. Because this is 1, -1 over 2, +1 over 3, minus, they're getting smaller, heading to 0. So what happened? It's a convergence. This, we can include x equal to -1. We can include it. Okay, so that's, I'm checking whether I need to really include x equal to -1. So I check yes, because at the end, when I, insert, when I substitute -1 into x, it was a turn, it turns out this series is alternating harmonic and it's a convergence. They're getting smaller, smaller, getting close to 0. But let's check when x equal to 3. So same thing, we do have this function, copy. So let me plugging in infinity 2 to the -n, n plus 1, 3 minus 1, and to the n. So it is going to be 2 to the -n, n plus 1, 2 to the n. So I can reciprocal 2 to the -n, 2 to the positive, n plus 1, and you have a 2 to the n. Ooh, they're going to cancel. So therefore, infinity n equal to 0, 1 over n plus 1. So watch me. As n increases, what happened? This is a 1 over 1. This is 1 over 2, 1 over 3. They're getting larger and larger. When x equal to 3, this power series is a divergence. When x equal to 1, we found out it is a convergence. This power series is a convergence. So what happened? You cannot include x equal to 3. We are only looking for the possible x's where this power series become convergence series. So therefore, the answer, we cannot. The answer will be what? Your x is going to be between -1, but do not include 3, which means -1, 3, open. That's your answer. So very important notation. I think it's not the right color, so -1. We do not include 3 because when x equal to 3, it is divergence. When x equal to -1, it is still convergence. So check this information. You need to check at the end. Everybody can do it. Oh, Professor, then maybe this is the answer. But you have to really check the beginning and ending number. Do we need to really include it or not? Okay, that's what it is. How you feel? Does it make sense to you? I hope so. You got this. We are accumulating all the learning you have learned so far. Awesome. So I'm going to give you guys a moment. If you got this one, I love to see your thumbs up. All right, so I think you guys got this. So this one would be in the final. I'm going to ask you find the, appropriate the correct x intervals. So many people just, finish up here. They don't check the -1 and 3 or whatever the ending number. Please check, okay? All right, so I'm going to give you one more example like this. Many people made a mistake. So if you got that one, I'm going to go down slowly. So we have the same goal. So we know what is going. I want to find out this power series is a convergence. So let's take a look at the an. An x minus 2 to the n over n plus 1, 3 to the n. An plus 1, x minus 2. N plus 1, n plus 1 plus 1, 3 n plus 1. So which means x minus 2 n, right? X minus 2 over n plus 2, 3n, 3. So I can, rewrite it with the an and an plus 1. Oh. So we got this. Are you guys okay? So I just modify, what I'm doing. X minus 2 to the n plus 1, I can break them in 2. x minus 2 to the n times x minus 2, because they have the same base. You can adding the exponent. And the bottom is n plus 2 and 3 to the n plus 1, you can break them into 3 to the n times 3. So anyway, we have an plus 1. Ooh, let's go to ratio test. So limit an plus 1 over an. So you're gonna do, we already know what the an plus 1. So x minus 2 to the n, x minus 2 over n plus 2, 3 and 3. This is an plus 1 times an, 1 over an. You have to flip over this. So top, bottom. Now I see all the cancellation. Where are you? 3n, x minus 2 to the n, goodbye. So therefore, limit all the remaining stuff. N plus 2, 3, and we have n plus 1. So we know what's going on. I'm going to bring the constant x minus 2 over 3, limit n plus 1 over n plus 2. So come on, guys. We know this is going to be what? The top degree, bottom degree, they're equal. So what happened? If you have a limit, top and bottom, same degree, you're going to reading the coefficient. So invisible 1 and 1, 1 over 1 is 1. So we have x minus 2 over 3 times 1, which is that this is your p. So we know when this p is less than 1, it is a convergence. So we're going to set it up less than 1. So you guys know the rest of story. X minus 2 over 3 is between -1 and 1, correct? Or there's equal. So we can multiply 3, 3, 3. So you're going to multiply 3 to get rid of the fraction. So -3. X minus 2, positive, adding 2 to 2. So we do have -1, x, and 5. Are you going to stop here? That's your final answer? Again, we found that, so the power series that we have, infinity n equal to 1. So that was a given power series, 3 to the n. It's a convergence when x is a -1 and 5. But we need to check. Do we really? However, we need to check the status of inclusiveness of x equal to negative. Do we really include? Okay. So let's do two scenario. I think I need a space. No, I don't need it. So now check. We're gonna check when x equal to 1. Check x equal to 5. Sorry, my iPad has a little bit of issue. Oops. Uh-oh. Please. Let me set it up again. Check x equal to 5. Okay, now what are you going to do? Plugging in, right? So we do have this copy. And I'm going to get rid of this. Ooh, okay, so you're going to plugging in 1. So infinity. X 1 minus 2 to the n, n plus 1, 3 to the n. All right, and then what happened? Actually, we have a -1, so my bad, it's a -1. So -1. So infinity, -3 to the n over n plus 1, 3 to the n. So I can separate, watch me, this part, we can separate it. We can separate it -1 to the n and +3 to the n. They're same thing. Yes. So therefore, n plus 1, 3 to the n. Got you. 3 to the n cancel. So we have -1 to the n over n plus 1. Oh, what is that? Just check the partial term. This is 1, right? If n is 1, it's a -1 to the 1 is negative. 1 -1 over 2. The next one will be, if you're plugging in 1, so they're going to be plus minus alternating. So what happened? If you look at this, they're getting smaller, getting close to 0. So this is convergence. So when x equal to -1, the power series, this, absolutely convergence. So we're gonna include it. We need to include it. Yes. Check x equal to 5. So here, I'm gonna plugging in 5. So 5 minus 2 to the n, n plus 1, 3 to the n. So 3 to the n, n plus 1, 3 to the n. Got you. There, cancel. So you have 1 over n plus 1. Oh, whoa. This is 1 over 2, 1 over 3. They're getting larger and larger. So they're getting larger. It's going to be infinity. So what does it mean? When x equal to 5, this power series is always divergence. So therefore, we do not include this. So your answer will be -1 include, do not include 5. So -1, 5, open parenthesis. That's your answer. So that's how you do 1.6, whether how to check on, whether the power series is a convergence and divergence. Does it make sense to you? So very similar, chapter 5 we did. And then I'm not gonna do the next question. You can try it. Who knows, this one is gonna be in the final, right? So try it, and I will just do one last example. So power series, we talk about the form, we talk about how to check whether it is a divergence or convergence, utilizing the ratio test, and this is very unique question. So here is the question, you can think about it. Use a power series for represent each of the following series F, find the interval of convergence. So basically in this question, this is your AN. They want to know, this is a series, power series. You're going to write this form, right? In this time, n to the third, because we have n. They want to know whether this is convergence or, when which n gives you power series, or if you feel confused, I can change this one, x. So infinity, x equal to 0. So that's the definition. I want to know when it is a convergence, correct? So same question, we're going to look at the ratio, we're going to use the ratio test, or you can think about the size of x. So hold on. So are you following what I'm doing? I want to find out the possible x's. Make sure that this power series is a convergence series. So sometimes you don't need to ratio test, because watch me, you can think about a little bit of different logical thinking. This means you can rewrite it 1 over 1 minus negative x to the third. How about that? Because a double negative changed to positive. Yeah, so I can just modify that equation, and then we know 1 plus x, x to the second, whatever. If you have a geometric series, or AR to the second, these are all the geometric sequence, because you keep multiplying x or the same common ratio. So to make sure this geometric series convergence, you check the first number minus the ratio, a over 1 minus r. This is the convergence formula, correct? So check it out. This is what? To find out the next number, you're gonna keep multiplying. So this implies more to find the next number, keep multiplying negative x to the third. That's exactly the form. This is 1 minus the ratio, common ratio r. Are you okay with that? So that's the r. You keep multiplying negative x to the third to find out the next one. You're gonna find out the next one, 1 minus x, negative x to the third. So this one should be x equal to 1, because I don't want to make you confused. We are using the x variable. So that's what's going on. So what happened? So the ratio, according to the geometric series, when the ratio is between or less than 1, it is always a convergence. So therefore, we're going to do that work. So the last one here, therefore, we know r equal to negative x to the third. So r absolute value is less than 1. That means negative x to the third is absolute value less than 1. So negative 1. And then here, I'm going to multiply negative 1 everywhere. So that 1, negative times a positive. You're going to switch over x to the third and negative 1. And then I'm going to plugging in third radical to get rid of the third power. So they are cancelled everywhere. So this is still 1, x, negative 1. So that's the possible x. When x is between negative 1 and 1, this power series, or this any type of series here, but this one is power series. This is series, or if you're confused, this is given series is convergence. So sometimes you don't need to use a ratio test. Sometimes you can use the characteristic of the geometric series. Whenever the common ratio is less than 1, that's going to be convergence. So according to here, you can modify and then find out the common ratio, which is a negative x to the third, and then utilize the concept of the geometric sequence convergence characteristic, then you can find out the interval for x. So that's it. And that's how we finish 6.1.